walk me through it. Okay, for the zeros, -5, 1, and 4. Does everybody agree? Okay, here and here and here. Zeros means the same thing as x-intercepts, right? So there they are. Okay, what about their multiplicities? 2, 1, and 2. How do we know? Okay, based on what it does at that intercept, right? This one bounces off, so again, like locally, it's like a tiny picture of the end behavior. Relative to -5, those ends are pointing in the same direction, which is like an even, degree. That means like locally that thing is even as small as possible then, so we assume it's 2, or if you want, like it looks like a little parabola. Here, crosses through, pointing in opposite directions then, odd, goes straight through like a line, multiplicity is 1, and then the same kind of thing's happening right there with the multiplicity is 2. We feel okay about that? Yeah, okay. Right on. What is the degree, even or odd? How do we know? Odd, how do we know? Okay. Okay, so a bunch of ways we can know. The ends are going in opposite directions, which tells me the degree has to be odd. It must say the thing about turns again. So how many turns are there? Okay. 1, 2, 3, 4. The smallest the degree can possibly be is actually one more than that then, like so you go up. So since there were 4 turns, the degree has to be at least 5. We can also, I think I heard somebody say something about multiplicity. You can also learn something about that by adding these, right? The sort of most direct thing, though, is probably the fact that the ends are pointing in opposite directions. Like that's the one that's maybe least likely to have, I don't know, some weird edge case thing where, it looks like it does one thing, but it actually does another thing. The end behavior, that part like can't lie to you, right? There can't be like hidden information there. So opposite directions at the ends. Is the leading coefficient positive or negative? Negative, how do you know? Yep. As x goes to positive infinity, the y values are going to negative infinity, or in other words, the right-hand side points down. I don't know how to write. There we go. Okay, and then what else? Factored form. Okay, write an equation in factored form. Assume that the leading coefficient is either 1 or -1, and the degree is as small as possible. So what would this thing look like in factored form with all those, details? Negative out in front, because we said the leading coefficient was negative. The leading coefficient's either plus or -1. In this case, it's got to be -1. I'm just going to park a negative sign out front. How many factors are we going to get? 3. How do I know there are going to be 3 factors? Because there were 3 zeros and you get a factor for each 0. And we're going to talk more about that today. What do the factors look like? X plus 5. That one's squared because of the multiplicity. X minus 1. That one's got multiplicity 1, so that factor just shows up one time, so I don't need to write anything on it. And x minus 4 squared. Okay, cool. And then we could, once we have a thing that we think is a pretty good guess, I could graph this in a calculator and check. Notice, though, again, like the scale here is kind of crazy, right? The y-intercept is like 400 and something. Because if you plug 0 into this, you end up with 16 times 0.5. So, like, it's kind of way up there, right? but that's what that looks like. Okay, cool. Everybody feel okay about that? Yeah, any questions? Okay, you can hang on to those, draw a smiley face on it or whatever kind of positive feedback you need, but I'll put the grade in later. Okay. All right. So this week, that's the wrong place. We're going to do two things. One is to kind of really reinforce this idea of how we've been solving polynomials. You need a copy of the notes for this week. I've got some extras here. And that's the factor theorem. So this is a thing that we've been leaning on pretty hard that, says that if we can factor something and set it equal to 0, then we can split the factors up and find the solutions to the problem or the zeros of the function. That's how we did the thing that we just did here. The fact that I can take these zeros and obtain these factors is because of the factor theorem. So last week, Thursday and Friday, we looked at a whole bunch of, different cases and different methods and techniques that we can use to factor things, right? Looking for a common factor, looking for ways to factor by grouping, or, rely on like a quadratic sort of structure to a thing and factor that way. Today, we're pretty much talking about, well, how do I factor the hard way, right? The idea is this: if we have, let's say, well, let me just point at this thing that I've already got. This is something that we could factor, normally, right? Like I know how to factor x squared plus 5x plus 6. Already it's x plus 2 times x plus 3. If we think about that as, an equation where I can manipulate and move things around, if I divide both sides by, say, x plus 3, it cancels out of the right, and on the left we get x squared plus 5x plus 6 over x plus 3 is equal to x plus 2. And I've rephrased this kind of fact that I know about how to factor this trinomial here into a division problem. If you take this and divide it by that, you get this. Well, that means if I, have a thing maybe that I don't know how to factor, but I do know some information about a thing I can divide it by, or its divisibility, then I can factor by, doing the division, physically doing the division. So even if my, factoring tricks and stuff don't work, this is how you would factor kind of the hard way, right? Similar to, the way you deal with that with numbers, right? If I say, hey, what's the square root of that? And I'm not sure, that might be a perfect square. Is 324 a perfect square? Yes, 8. Dang it. Okay, 320, which is not a perfect square. And we needed to do the, simplify the radical thing, right? Well, what I need to do is factor it, right? Well, to start factoring that, I just start wherever I see. Like, I don't have to jump straight to what the prime factorization is. I don't have to look at this and know, oh, that's 2 times 4 times 4 times 2 times 6 times 5. Like, I don't need to know that right off the bat. Only like half of those were prime numbers. That was a terrible one. But I start with something that I do see, right? So what do you see about 320 that we could divide into it? 2, okay, because it's even. And then, I get smaller and smaller chunks of the thing until finally, like, we end up with the prime factorization, right? That's how we go through that. I don't have to start with 2. I can notice that it ends in 0 and say, oh, 10 must go into it, right? We just start somewhere and then kind of follow it through. So what we're going to be talking about today is kind of a related idea. I'm going to start with something that maybe I don't know how to factor. And again, I know that, like, we do know how to factor this one, but I'm going to start with something that maybe I don't know how to factor, and some information about something that goes into it.
And then I'm going to like manually do the division to figure out what else goes into it, right? A little bit of terminology stuff, just as a reminder. The thing you're dividing is called the dividend. The thing you're dividing by is called the divisor. And the answer is called the quotient. Well, I'm just probably going to say the words. So yeah, like there's not going to be a vocab test later or something, but I'm going to throw around the words divisor and quotient and stuff. So quotient's the answer. That's probably the most important part, right? When you do a division. Okay. So the video that I posted for this week that surely you all watched covered how you do long division and how you do synthetic division. So what we need to do is practice with that. So here are some problems. Start with A. So I'm gonna, just go to where I have some room, but okay. This is an algorithm. It's a computational method, right? We haven't had a whole ton of places so far this semester where we've needed to like get into some kind of really gritty like calculation stuff, right? That's going to happen now. So this is a place where we're going to want to like work a little bit slowly, a little bit deliberately, because if you make a goofy little arithmetic mistake at the beginning, it just sort of spirals and like throws the rest of it off because it all depends on the step that came before. So I'm going to do this by long division and by synthetic division. Again, they're pretty much interchangeable. Basically, you can do one anytime you can do the other. There's a little bit of a catch to that we'll talk about. But here's what this looks like by long division. So I want to divide x plus 4 into x squared plus 2x minus 3. Thinking about long division with numbers, kind of like what we saw here. The way we do things is to first look at how this goes into that, right? The whole point is to break the thing up into smaller pieces so I don't have to look at, some, I don't know, 3-digit number or something and go like, oh, I know exactly how many times 15 goes into that, right? I just break it up into smaller chunks and take it one thing at a time. And there we go. So for polynomials, what that means is that we're going to look at how the leading term divides into the leading term. So for starters, I just kind of ignore all this other stuff, and I'll let those details work themselves out as we go. But I start with asking, hey, how many whole times would x go into x squared? So what do you need to multiply this by to match this? X, right? Because x squared is x times x. So if you're dividing that by x, what you would be sort of missing or get back is just x. So you got to match the power and the coefficient, right? So the idea is, what would this need to be so that when I multiply by this, I get exactly this back? Okay, so x times x is x squared. So once we've got that sort of first part, like how many whole times would this go in, I'm going to take this and multiply by that. That's multiply, which is x squared, and carry it down. X times x is x squared. Notice that these are identical. Those match exactly. That's good. That's kind of the whole idea, right? For reasons that'll become clear in a second. But now I'm going to stop completely ignoring the whole thing that's there and do the whole multiplication. So x times x is x squared. What's x times 4? Yeah. So what we did is take X copies of this thing out of the dividend, the thing that we were dividing. What we need to figure out is what's left, right? Just like if you're dividing, I don't know, let's maybe do a like number division right next to it. If I want to divide 40 by 3 by hand, what I do is start by looking for, you know, if I don't see it and don't jump to it right away, I start by looking for, well, okay, how many times does this go into that? Once. 1 times 3 is 3. So we subtract and see, okay, now what's left that I still need to deal with, right? 3 is going to go into 40 at least 10 times. And then let's see what else we need to, you know, account for. X plus 4 is going to go into this at least X times. Now let's see what else is left over. So when I subtract X squared minus X squared is 0. That's good. That was the whole idea. Those are supposed to drop out. 2X minus 4X. And then negative 3 minus, there's nothing there, so 0. That's one step. Yep. How'd I get the 4? X times 4. Yeah. So it's this times this whole thing times that whole thing. So X squared plus 4X. Subtract, those drop out. 2X minus 4X is negative 2X. Negative 3 minus nothing is just negative 3.
Okay, I'm sorry, why is X squared plus 4X negative?
It's so we're subtracting it to see like what's still left over, right? So like in the same way here, this is the tens place. So I'm not really subtracting 3, I'm subtracting 30 and seeing what's left over, right? So 3 goes into 40 at least 10 times. And then, okay, that leaves 10 left over that I'm still gonna have to deal with. This is saying X plus 4 goes into this at least X times, which would give you this. Now what's left over to still deal with in like lower order stuff. Okay. That's one step of the division algorithm. Then you do it again. So now we look at, again, this and the leading term of the stuff that's left. So how many times, or what would I need to multiply X by to get negative 2X? Negative 2. That's the next piece of the divisor, or the quotient then, negative 2. Maybe switch colors for doing like the next sort of step. So negative 2 times this. Negative 2 times X plus 4, what do you get? Negative 2X minus 8. Subtract. Negative 2X minus negative 2X. This is, again, where we want to start, like, you know, being careful, being deliberate with that. Negative 2X minus a negative, so add. So negative 2X plus 2X. 0. Yeah. Which is good because those ought to drop off, right? Like, if those don't, the leading term doesn't drop off at each step, it means that I probably didn't take the right thing here because I sort of didn't get all of it. So the order, the degree of the term kind of plays the role that place value does when you do division with numbers. Okay, so that's 0. Negative 3 minus negative 8 is 5. Okay, now, if we're doing this with, you know, real numbers, I look for how many times 3 goes into 10. 3 times. 3 times 3 is 9. I subtract, I get 1. What does that mean? It's a remainder. Yeah. 3 goes into 40 13 whole times and it leaves 1 left over. Now, if you want to do like a decimal, you add a decimal point, you write a 0, and you carry it down, you keep going until, you're satisfied, I guess. Or as soon as there's nothing left to carry down and this doesn't go into that, we have the remainder. The equivalent thing here is that our divisor is degree 1, right? Its leading term is x, which is bigger than this constant thing. There's nothing left to carry down. X doesn't go into 5 a whole number of times, so this is the remainder. Once the degree of whatever's here is smaller than the degree of the thing we're dividing by, we stop. That's our remainder. What this means then is that, oh, sorry. Thing got away from me a little bit. What this means is that this is equal to x minus 2 with remainder 5, which means there's a fraction part that you can write like that. That's the quotient, the whole number part of the answer. That's the remainder. So I mean, if this was negative, then you could write it as minus. But yeah, it's the same idea as here saying that 40 over 3 is 13 and 1/3. So think of that plus sign like an and, right? Okay. Same thing, but with synthetic division. Synthetic division basically just says, okay, hey, all that stuff that we just did, we're going to do the same thing, but I don't want to have to write that much stuff down because that kind of felt like a lot. So if we know the place value, right, where the terms are and what the terms are, if I can preserve that using the order, right? So we're used to looking at things in descending order, the square term and the linear term and the constant term. If I can preserve that using just where I place them, right, writing them in order, then all I really need to know are the coefficients. So the coefficients of this, think like A, B, and C, are 1 and 2 and -3. So 1 and 2 and -3. Then for reasons that'll become a little more clear in a minute, when we kind of circle back to like where we're going with this. We're dividing by x plus 4. Synthetic division only works for linear divisors, so this has to be linear. So it's got to look something like, x plus 4, x minus 2, or, x minus 1 or whatever. But since this thing is linear, the 0 that this would kind of correspond to would be -4, right? If I took x plus 4 and set it equal to 0, I would get -4. That's the thing that goes right here. That's going to act like the divisor, sort of the information that we take from the divisor. I'll say this again, I said this in the video too, but synthetic division is a little more artificial, so it goes a little faster. It feels more efficient, but it's also going to feel a little more like, why does this happen? The reason why it happens is because it works. Either way, though, it's going to be something that like you're just going to have to do a few times before it really clicks. But synthetic division, we carry down. So start by just bringing that down, which is 1. And then multiply. -4 times 1. You store that there. And then we do the same thing, but we add down the column. So I'm working here now. 2 plus -4, -2. We kind of move over, but we still multiply these things. -4 times -2, 8. And so that goes there, and then we add down the column again. -3 and 8 is 5. Once we run out of stuff, we're done. That's the remainder in that last position. And these are the coefficients on the quotient. So these tell me that the quotient, and this is why synthetic division works, because we're dividing by a linear term, right? Divided by x plus 4, which is degree 1. What's going to happen is that whatever you started with, which in this case was quadratic, you divide out a linear thing that subtracts 1 from the degree, right? So 1's degree 2, we're taking 1 away. This is linear. These are the coefficients. So the quotient is x minus 2 with remainder 5, which is the same thing we got before, which is good news. That means these both work. Now, again, synthetic division only works for linear stuff. So it's not quite as general. It's not quite as like applicable. That's a hard word. You can't use it for as much stuff. But it does work for linear things. And the thing that we mostly care about, i.e. the thing I'm going to ask you to do on an exam question, is to use a linear factor to factor a thing. So if you like this better, you're going to be just fine, like sticking to synthetic division. If you like long division better because, it's a little more in sync with like stuff you already know and, kind of explains itself a little bit better, that's cool. I don't really care how you do it. You just need to be able to divide stuff. Right? Sure. I mean, you might not love it, but if you took this whole thing and multiplied by x plus 4, you should get this back. So you would, like distribute this thing through to a, FOIL type expansion thing, and you should end up back with that. That's how you would check. Okay. Whew. This is a thing that, watching me do over and over again is not really going to like take you very far. Like you just have to, try to work through some on your own. So do these tonight as practice. I want to spend a few minutes though talking about why and when we would do this. So take a look at the remaining examples, 2, 3, and 4. They all have basically the same statement. Given that something is a zero of a function, find the other zeros. So really what we're trying to figure out here is the zeros of this. So we're trying to solve that. And the problem is that if you think about this thing, and think about, the methods we have for solving higher degree polynomial equations, nothing's going to work, really, right? There are no common factors. It's degree 3, so I don't have a good, like, just, plug and chug formula. I see 4 things, so I might think factoring by grouping, but anything I take out of this, I'm not going to be able to match by, taking things out of this, right? The common factors aren't going to like line up in such a way that I can get grouping to work. If I get like really creative and try to look at this as a, parts of a binomial expansion. We might be able to, reason our way through that, but that might get a little bit messy. And but if we know one of the zeros, so I'm told that 2 is a 0, meaning if I plug 2 in, 8 minus 24 plus 6 plus 10, I get 0. But if I know a 0, then the factor theorem says that we know a factor also. If 2 is a 0, what's a factor of this this equation? X minus 2. Exact same thing we did, 20 minutes ago with the quiz question, right? You find the zeros, that tells you about the factors. Okay, now I'm telling you, hey, this is a 0, so tell me what a factor is. That means that somehow this thing factors as x minus 2 times, well, I don't know, but it's equal to 0. And if this was degree 3 and I split off a linear degree 1 factor, what would this be? What would its degree be? What kind of thing would it have to be? If overall the thing's degree 3 and you take out a linear thing, the thing that would be left would have to be degree 2, right? We call those quadratics. What do we know about quadratics? Right, exactly. Okay, so if we can figure out what this stuff is, then we're good to go. Well, here's how we figure out what that stuff is. We need to divide x cubed plus, I don't remember what it was, minus 6x squared plus 3x plus 10 by x minus 2. The original function by this factor since we were given a 0. Okay. Since we know a 0, we know a factor. That factor is linear. That means I can use synthetic division, which I assume we're probably going to be, happier with anyway. So I'm going to divide this by this. Again, I'm going to take the coefficients here. So 1, -6, 3, and 10. And I'm going to divide by x minus 2. So start by carrying down. Then multiply. 2 times 1 is 2. That goes here. And we add down the columns. So I'll pause for a minute and let y'all continue. Okay, did you get that? 1, -4, -5, and then 0 in the last position. Okay, cool. What does that mean? First of all, here's a built-in little, like check. Okay, stop. What does the fact that this is 0 tell us? That there's no remainder. Hey, did we already know that going in? We started with a 0, which means we know a factor. Being a factor means that you go in evenly, right? Like 4 is a factor of 8. 3 is not a factor of 8 because it doesn't divide in, right? If this is a factor, it has to divide in evenly. This 0 almost certainly means that we did the division right. It's very unlikely that I goofed up the division somewhere and still got remainder 0. Again, asterisk, like it almost certainly means we did the division correctly. But that's a good sign. That means that this expression we were trying to factor, x cubed minus 6x squared plus 3x plus 10, is x minus 2 times what? X squared minus 4x minus 5. The original thing was degree 3, right? So it had, 4 terms, the cube, the square, the linear, and the constant term. We divided out a linear thing, which means these are the coefficients on x squared and x and the constant term and the quotient. Which means that if I want to set this equal to 0, and I can factor it like that, our old friend, the zero product property, says that either x minus 2 is 0, so x is 2. Well, hey, we already knew about that one. Yeah, cat, sorry. Where did I get the square here? Okay, so the original thing was degree 3, right? And we divided by a degree 1 thing, right? Divided it by x. So ignore all the other stuff. X cubed divided by x is x squared. So that first term we got is the coefficient on the x squared term. And then, just sort of walking down from there. Yep. So either x is 2 or x squared minus 4x minus 5 is 0. Which is quadratic. We're setting it equal to 0 and solving. So we know how to do that. Just for the sake of time, I'm going to factor that one. So 5 and -1 are the other zeros. Right? If you go back to the original question, given that 2 is a 0 of this thing, find the other zeros. These are the other zeros, right? Total of 1, 2, 3. We already knew about this one. Okay, so that's factoring a thing that we don't know how to factor otherwise because none of our little factoring tricks and stuff work. So instead, we take some piece of information, in this case, a 0 that we were given, and factor it by dividing, right? Like brute force factoring. Okay. All right. Well, that's it for today. There are 1, 2, 3 other examples there in problem 1 that we didn't get to. And then 3 and 4 are 2 more examples where you're sort of working the full thing out. Right? Do the division and then try to solve. We'll spend some time tomorrow, going over this, maybe do another one, answer any questions you might have, and then we'll start kind of reviewing, the whole thing. So go home and do some problems. I'll see y'all tomorrow.
And I was accelerated math, so I had one day today. I've been one day on it, that's the next step.